solving differential equations using integrals. All right, of course, we have a lovely class on this stuff, Math 255 on Crown Jewel. I think that's the end of your journey here at Mesa in math for many of you. All right, differential equations. So, for example, all right, let's say Mr. Burns dies and he gives me $1,000. I inherit $1,000. All right. I inherit $1,000. All right. Now, let's say that a computer spends the money for me. All right. After T years, or T years when I inherit the money. After T years, I spend it at the rate of $10T per year. Okay. I spend it at the rate. Let me double underline rate. Okay, when you think rate, what are you thinking? What keyword? Derivative, right? Rate of change, right? Rate of change. I spend it at the rate of $10T per year. All right. Well, what would be an interesting question? How long until I run out of money? Okay, let's assume I don't go into debt. Okay, how long until I run out of money? Okay, how many years will it be gone? Okay, or you know, when will I run out of money? When will it all run out? All right. When do I run out of money? Okay, so Brewster's 1,000, I guess. All right. First of all, let's set this up. Okay, let's set it up. Now, there are two ways that you can model it. Okay, so we're going to define a function here. All right, we're going to define a function little f. All right. Here, I'm going to let little f of t, because it's going to be a function of time, right? We're going to let little f of t be the amount of money in dollars left in my account after T years, or T years after I inherit it. All right. So I'm going to let f of t be the amount of money left in my account for this inheritance. Now bear in mind, you can just as easily set it up where f of t is the amount of money you've spent, and that's fine. That's perfectly okay. Let f of t be the amount of money here. It's the amount of money left in my account T years after I inherit it. All right. Now, instead of f of t, we might call this y. All right. And there are different notations we can use, right? We can use f notation or y notation. All right. So, what is the differential equation we have to solve? All right. Solve the diffie-q, and differential equations are known as diffie-q's. Computer scientists might object. They might say, well, let's say, why not difference equations? But differential equations are more common. All right. Solve the diffie-q. All right. Now, rate, we think derivative, right? F prime of t. All right. Now, you might think F prime of t is $10T per year, but there's something we have to do. F prime of t is what? If f of t is the amount of money I have remaining in my account, and I'm spending the money at $10T per year, what's f prime of t? Negative $10T per year. Please keep the sign in mind. Now, bear in mind, if you would set up little f of t to be the amount of money you spent, then you would not have a negative sign. So whatever you do, make sure you're consistent. Okay. Here, this is the amount of money I have remaining. Okay, and I want to know where it's going to be 0, right? Okay. But if that's the case, then f prime of t will always be negative, all right? Because I'm spending. That means that my account's decreasing. I'm assuming that I'm not depositing anything further, okay, beyond the inheritance. All right. So there's not a differential equation. At the same time, I'm going to show you the y notation. Okay. Instead, we could say dy dt, right? That's another way of expressing a derivative. That's Leibniz notation. Dy dt. That's Lagrange notation. This is Leibniz notation. Dy dt is negative 10t. All right. All right. Now, so is that me? subject to. Turn off the phone, huh? Oh. No one calls me now. All right. Okay, subject to an initial condition. Subject to the initial condition, or IC. All right. Because we need some more information here. All right. Well, I inherit $1,000. What does that mean? In notation, what does that mean? I inherited $1,000. Okay, what's 1,000? What of zero? What of zero? F of zero. F at zero, right. Subject to the initial condition, F at zero is 1,000 American dollars, all right? F of zero is 1,000, okay? Well, at time zero, that's when I get the money, I get $1,000, right? At time t equals zero. All right. Or in the Y notation, okay, Y is 1,000 when $1,000, that's $1,000 when t equals zero. All right. Most of you will prefer the Lagrange notation. All right. Okay, so we have to solve this differential equation subject to that initial condition. All right. Because obviously it's going to depend, right? I mean, the way when we answer this question is going to depend how much money I started with. All right. Now, let's find the general solution. Find the general solution of the differential equation. All right. So here we're just going to focus on the derivative here. We're not going to worry about the IC just yet. All right. Later on we're going to have more than one, by the way. Right. We're going to find the general solution of the following. F prime of t equals negative 10t. All right. So here, I'm basically giving you the derivative, right? I'm giving you the derivative, and you have to find an appropriate antiderivative. All right. So what are we going to do to both sides? It's an I word. What's the I word? We're going to integrate both sides with respect to t. All right. So we're going to integrate. Okay. From now on, I might just write this, like the squiggle. All right. Integrate both sides with respect to t. Okay. We use this in chapter 3 also, right? With respect to t. All right. By the way, when you go to Calc 2, and I've heard Calc 2 professors complain about this, if your Calc 2 professor writes down on the board, please don't ask in class, what does that squiggle mean? That'll really embarrass me and you. All right. So this means integrate. All right. It's an integral sign. So let's do it. Okay. Let's integrate both sides with respect to t. The integral of f prime of t dt equals the integral of negative 10t dt. Meaning that this guy's antiderivatives will be the same as this guy's antiderivatives. Okay? Remember that an integral, an indefinite integral, corresponds to a family of antiderivatives. Okay. Assuming there are some. Okay. There will be. Okay. So when we integrate f prime of t, well, what do you think we get? When we integrate f prime of t, we're going to get f of t plus a constant of integration. Now the thing is, if we put a big old plus c over here, that takes care of it. Because you can argue we get a constant coming out of here, a constant coming out of there. Well, the bottom line is, if we put a big old plus c over here, that'll take care of both of those. Okay? So f of t equals, plus c. All right, that's fine. Okay. Over here, integrate negative 10t. Well, let's do it. The negative 10 pops out by linearity, right? Negative 10 pops out. When you integrate t to the first, remember, integrate. When you integrate t to the first, what do you get? T squared over 2. T squared over 2. That's the power rule for integration. Okay? Remember, if you raise the exponent by 1, divide by the new exponent. Okay, so like I keep saying, know the difference between taking a derivative and taking an integral. Okay, that's a good test. That's to see who passes the class and who doesn't. Seriously. Alright. Alright. So what is little f of t? Little f of t equals I'll circle that as a general solution. All right, f of t equals negative 5t squared plus c. All right, and that's going to correspond to a general solution. By the way, parallel to this, I'll go ahead and do the y notation because in differential equations in 255, you should get used to this also. Right? If we use the y notation, okay, we have dy dt, we have dy dt equals negative 10t. And then you perform what's called a separation of variables. Okay. A separation of variables. And we write in differential form dy equals negative 10t dt. You might be asking, did we just multiply both sides by dt? And calculus professors will debate on that. Some people would say, well, that's not quite the right thing to say. But others will say, well, it's differential form, so in that sense it's okay. If you think of this as a quotient of differentials, you'll get debate on that. But, formally, officially, we can write something like that. Okay, that's called differential form. Right? This is in differential form. And we use that. In 5.2, we're going to use it a lot. Okay, so we are going to write stuff like this. dy equals negative 10t dt. But again, a lot of people might argue that you shouldn't say that we're multiplying both sides by dt. That's a bit awkward to some people. Anyway, and then we integrate both sides. Right? Integral of dy, integral of 1 dy equals integral of negative 10t dt. All right. What's the integral of? Oh yeah. Meaning that I'm just showing you another way to write this out. The or is between the Lagrange notation and the Leibniz notation.
So it's the or of this?
Yeah, all of this stuff. Or you can do it this way.
Oh, okay.
Yeah. All right. Whose derivative is 1 with respect to y? Whose derivative is 1 if y is the variable derivative? Y. If you integrate 1 dy, you get y. Big old plus c at the end. Integrate negative 10t. Well, by a similar scheme, right? Okay, we're going to get negative 5t squared. Okay. You can ask the same question. Whose derivative is negative 10t? You might be able to figure out it's negative 5t squared. Okay, but basically it's the same thing. Okay, f of t or y is negative 5t squared plus c. Okay, that's our general solution. Questions about that? Questions? So what do we have so far? We have a family of antiderivatives. Here's t, here's y equals little f of t. Now, what's the graph of, for example, y equals negative 5t squared? What's the graph of that? It's a parabola opening downward. What is the, if you add 2, 5, 10, 100, 1,000, what happens to the parabola? Shifts up, okay? So what are we talking about here? We're talking about a family of quote-unquote parallel parabolas. Now, officially, we're not supposed to talk about parallel parabolas, but I think you get the idea. We get these parabolas where we have the same slopes, right, for corresponding values of t, right? In that sense, their derivatives are identical. All right. Now, here's the question. Which of these parabolas is the one that I want? Okay, I'd like to know what the plus c is. I just did my taxes this past weekend. Okay, what if your tax advisor says, okay, I figured out your tax. It's $200 plus c. And you ask, what's c? And your tax advisor says, oh, I don't know, some arbitrary number. You'd fire that person, right? Okay, I mean, that's, okay. So here, for this particular problem, and to answer our question, we have to know what that value for c is. Well, what have I not used yet? I have not yet used the what? The IC, the initial condition. We need the initial condition to identify these parameters. All right. And later we're going to have 2 parameters. All right. So step 3, use the initial condition or conditions. Okay, later on we'll have 2. Okay, use the initial condition or conditions, okay, to find C, and so forth. D, E, F, whatever. You would just have C. All right. In other words, find particular solution. Find the particular solution to the differential equation. Okay, so I use that panel just to say what we're doing. All right. All right. So we have f of t equals negative 5t squared plus c. You don't have to repeat that, but I'll just emphasize that. All right. Now, the initial condition when was time t was what number? T was 0. We're calling t equals 0 the initial time. All right. So we're going to plug in t equals 0. Now, folks, bear in mind, when we talk about initial conditions, they don't have to take place at time 0. It doesn't even have to be time. Okay. But it could have been t equals 0, t equals 1, t equals 2, t equals pi, right? Whatever. Before I run out of money. Okay. But bear in mind that the initial condition does not have to correspond to time 0. It could be some other variable, and it does not have to be 0. Okay. It's just additional information. It's particular information. Okay. So we plug in t equals 0. We get f of 0 equals negative 5 times 0 squared plus c. What was f of 0? It was $1,000. Okay. Equals, well, this is just 0 over here. All right. Equals c. C is 1,000, right? $1,000, all right? So we found out what C is. All right, and what do? Plug it back in. Okay, please remember to do that. Okay. All right, so then we get that, well, look here. In fact, I could, well, I'll circle this also. F of t equals negative 5t squared plus, we now know it's 1,000. And I now know which of these parabolas I want. I want the parabola whose vertex is at 0, 1,000. All right, so I want, so I want this guy here. Well, let me say it's this guy. Actually. Well, here's the deal. I want this parabola, all right, where the y-intercept is 1,000. Okay, it is in dollars, right? But bear in mind that negative values for t don't make sense. So really, I shouldn't be graphing that part. And let's assume that I'm not allowed to take loans or go into debt, so I don't worry about this part either. So really, for all practical purposes, we only care about quadrant 1. Okay? And again, we haven't yet answered the question. What's the question that we're asking? We're asking, when does what happen to me? When I run out of money. When f of t is what number? 0. $0, yeah. So I want to know the t-intercept, right? I want to know the positive t-intercept.
How come we don't do the negative?
Oh, well, I'm just assuming for now that I don't take out loans, I don't go into debt.
Okay.
Right? Okay. When I run out of money, and I'm not allowed to take out loans or anything. Right? Okay. Bottom line, we want the t-intercept, the positive t-intercept. Okay. In principle, you don't even have to X that out. But, there are other problems where, you drop a ball, and the assumption is that when the ball hits the ground, it doesn't burrow in, like Phantasm. It just stays on the ground. It rolls. Right. Nobody watches Phantasm? Right. That's those killer balls. Fine, right. Okay. Let's see. All right, we got to answer the question. All right, got to answer the question. Number 4. Well, to answer the question, we have to solve the following equation. Okay. Solve f of t equals 0, or $0. Okay. And of course, we know that t is non-negative. Okay. We only want the positive or non-negative value for t. All right. Let's solve f of t equals 0. The positive real solution for that. What's f of t? It's this thing. Negative 5t squared plus 1,000 equals 0. At some point, you have to identify what c is, right? Okay, let's subtract by 1,000. Right? Negative 5t squared equals negative 1,000. Divide by negative 5. T squared equals positive 200. All right. T equals plus or minus root 200. And if you care to simplify, 200 is 100 times 2, so the 10 pops out, all right? t equals plus or minus 10 root 2. Of course, the negative root we're no longer considering, right? Because negative values for t don't make sense in this problem. All right. If you round that up, by the way, that's about 14.1. All right. So t is going to be about 14.1 years. Okay. So when do I run out of money? I run out of money in about 14.1 years. All right. So this here turns out to be 14.1 in years. All right. And then after that, the model's no good. I assume that I've run out of money, I'm running a barrel, and I can't take out any loans. Right. 14 years, not too bad. Stretching that out. All right. Any questions? Any questions? About 14.1 years before I run out of money, and the model's good up to there. All right. Any questions? Any questions? So I hope my financial advisor wasn't calling me saying you lost all your money. Remember that guy in South Park? And it's gone. I'm dreading that call. It's all gone. All right. Any questions? Any questions? Solving differential equations. So the idea is that you're given information about a rate, and you're given some other bits of information, and then from that, we're trying to reconstruct the original Big Daddy. Okay, so you're trying to reconstruct the Big Daddy from this other subsidiary information. All right. Questions? Questions? So that's the particular antiderivative I want, and then I can answer the question. All right. Okay. Well, that's an example of a first-order differential equation because we only had to go down to f prime. Sometimes you have to go down to the second derivative, and those are called second-order differential equations. All right. So, but in order to do these, we typically need not just one IC, but two initial conditions to do a second-order differential equation. All right. All right. Example. Okay. Solve the following. Solve f double prime of x equals 4. Oh, that looks nice. Well, it turns out this still will be some work, actually. All right. This is a second-order differential equation because there's a second derivative there. Second-order differential equation. All right. So it's kind of like order is to differential equations what the degree might be, right, for polynomials. But the second degree is 4 everywhere. It's constant. Okay. Subject to. Like I said, we're going to need two initial conditions here. All right. Subject to f prime of 2 equals 1 and f of 2 equals 3. And these are our ICs, our initial conditions. Bear in mind that we didn't have to have these be the same number. I could have given you f prime of 2 and f of 6, for example. Okay, so it didn't have to be at the same number. Okay. And there are other problems called boundary value problems, where you kind of pin the graph down, where you're given two function values, okay? And then you got to kind of connect the dots. Although those often require computer approximations. Those are harder to do. They often involve computer approximations, numerical analysis. All right. This one we can do analytically. All right. Okay. So solution. Right. Well, what do we mean by solve that? It means that we ultimately want the Big Daddy. We want little f of x. All right. What do we want ultimately? We ultimately want a rule for little f of x that will satisfy all these conditions. But before I identify little f of x, we're first going to have to identify what? F prime of x, right? We're given the second derivative. Let's find the first. And then this guy will help me out. Not this guy, but this guy will help me out. All right. So first, let's find f prime of x. All right. Let's find f prime of x. Okay? Well, what do we start by doing? We take this guy and we do what to both sides? we integrate both sides with respect to x. All right, so we're going to integrate f double prime of x with respect to x. Remember, whenever you have an integral sign, you need a d block, right? Okay, equals the integral of 4 dx. All right, when you integrate f double prime of x, okay, we get f prime of x, and then the whole plus c jazz. I can go over here. All right, this might be an easier question to answer. Whose derivative is 4? This confuses me. Whose derivative is 4? 4x. Okay, and then the constants absorbed in x. Okay. So 4x plus c. So bottom line, you need that plus c guy when you remove all the integral signs, all right, with their attendant dx or whatever, dx or dt has. All right. Now we have the general solution for f prime of x. We now need to use an IC to find out what c is. All right, that's why we need these initial conditions, so we can identify these parameters. Okay, so let's find c. I'll sort of circle this. Okay, let's find c. Okay, well, in particular, we're curious what's up when x is 2, right? We were given information about f prime of 2, so I'm going to plug in x equals 2. When I do that, I get f prime at 2 equals 4 times 2 plus c. So folks, c is not always these numbers that you're given, okay? Because, for example, you might have to plug in a number other than 0, and sometimes you will be dealing with polynomials. For example, e to the 0 is not 0, it's 1, right? Cosine of 0 is not 0, it's 1, right? So you don't always get 0 for this piece over here, right? Here we will have to do some arithmetic. Sorry. We're given that f prime of 2 is 1. 1 equals 8 plus c. Turn around. C equals, subtract 8 from both sides, negative 7. Okay, what do I have to do? Or what should I really do? Plug it into here. Okay, you have to do that at some point. All right. So when we do that, we get that. F prime of x in its full glory is what? 4x minus 7. All right, so we're up to there. Okay, I think it is a good idea to oval or circle in these things. F prime of x is 4x minus 7. Any questions? That's f prime of x. Take your time. Not too bad, just take your time. But I don't want f prime of x as my final answer. I want little f of x. So, what do? Once again? Integrate both sides, once again, with respect to x. I'll do that over here. And we're going to find little f of x. Alright. Find little f of x, which is our big daddy. Alright. I'm going to integrate both sides of that with respect to x. The integral of f prime of x dx equals the integral of, I need grouping symbols, because whenever you integrate something with more than one term, you need to put grouping symbols. 4x minus 7 dx. Alright. When we integrate f prime of x, we get f of x. And you know what? I don't think we should put plus c. Why not? We already used c, and we're not guaranteed that it's the same number. So really we should use d here. Okay. Now some of you might argue, well, wait a minute. I mean, weren't we very liberal with using c before? Well, here we're going to identify them as particular numbers. So if d's not negative 7, we really should indicate that that's a different letter. Okay. It could be negative 7. We don't know yet. But yeah, it is general practice to use a different letter at this point. Plus d. All right. Now we're going to integrate term by term. Okay. 4 times, how do you integrate x? X squared over 2. Okay. Minus, whose derivative is 7? 7x. Ironically, these are the ones that get people. Okay. It's funny because people can integrate x to the 100th, but they have a hard time integrating guys like these. All right. Let's clean this up a bit. F of x equals, this is 2x squared minus 7x plus d. Okay, and that's our, well, sort of general solution for the f of x. We have to find d. To do that, we need to use a what? An initial condition. Yeah, that one we didn't use yet. All right, so let's find d now. Let's find the value for d. Okay, now remember, I gave you information information about f of 2. So we're going to plug in x equals 2. Again, it didn't have to be the same number as before, right? I could have given you f of 6, for example. But here, I gave you f of 2. Right. So we have f of 2 equals, plug in 2 to the right, 2 times 2 squared minus 7 times 2 plus d. Plus d. What's f of 2? We gave you that was 3. 3 equals, this is 8 minus 14 plus d. I trust you can do this. D equals, okay, well this is negative 6 over here. Add 6 to both sides, you get d equals 9. Alright. D equals 9. What do I have to do? Plug in, don't lose that point. Okay, go ahead and plug that in. And we're going to get our big daddy here, little f of x. So from all this, we get that little f of x equals 2x squared minus 7x plus 9. And I'll box this in. That's our solution. 2x squared minus 7x plus 9. Any questions? Okay.
How come you don't put, how do we improve 1 other than 3? Remember in the beginning put f of, get rid of 2 plus 1, and then you have 1.
Yeah, but here I'm using the fact that f of 2 is 3. Okay, before we used f prime of 2, now we're using f of 2. Because this is a form for f of x. Before it was a form for f prime of x. This is f of x. So we use f prime of 2 to help us with f prime of x. We use f of 2 to help us with f of x.
I wrote it down.
Right. And bear in mind, I will typically give you the a derivative value and an original value. You usually don't get a boundary value problem. Those tend to be a lot harder. And you can check this, right? You can check to see. You can check to see, does f of 2 equal 3? Does f prime of 2 equal 1? Does f double prime equal 4 anyway? You can check all those things. Any questions? Any questions?
If you're trying to find like the third, so we do like C, D, and then.
There's a thing. You got capital E, yeah. 3 initial
Okay, so
conditions,
just keep
yeah,
going.
yeah. And I'd be giving you a second derivative, a first derivative, and an original value. Right. Okay. I suppose there are situations where maybe systems might come into play. Right. Okay. Questions? All right. Okay, so by the way, what information am I giving you here? So, based on some very limited information, you can actually grow a function, right? So what's happening here? All right. Okay, now, oh, by the way, how do you graph this? How do you graph a quadratic with a positive leading coefficient? That's an up parabola. It turns out to look kind of like this. All right. And what am I giving you? I gave you that f of 2 was 3. Okay, and what does that mean? What does that mean regarding the graph? The point 2, 3 lies on the graph. Okay, turns out that's a little bit to the right of the vertex, turns out. So here's the point 2, 3. All right. I'm also giving you that f prime of 2 is 1, right? F prime of 2 is 1, right? And what does that tell us? It's sloping upward, right? Tangent line is slope 1. So this tangent line has slope 1. Okay, and in fact, I'm giving it to you right here. Now, bear in mind, as I said before, I could have given you like f of 6, right? So the point's over there. So I might give you a point here and a tangent line slope here, for example. Okay, so you might get different packages of information. Here, we're tearing apart one point. Okay, and I gave you the concavity, right? F double prime of x is 4. Well, you know that the guy is concave up everywhere. But basically that tells us how we're growing. That's like a seed here, right? Okay, and this tells us how this guy's growing away from the tangent line. All right, so that's all enough information for us to decide that this was in fact the original Big Daddy function. We had enough information. Now again, if we have a third order differential equation, then we have a more complicated guy, right? Okay, there's more detail there. All right. Questions? So given limited pieces of information, you can go to Big Daddy. Any questions? So in practical applications, what is a common second derivative that we see in applications? We have position, velocity, acceleration. All right. All right. And then next would be the jerk, by the way. Again, I'm not kidding. All right. So let's do a physics problem, a basic physics problem. By the way, some good news for you folks. This Wednesday, that's Wednesday, that's the last time in this class when you're going to get a complicated word problem on an exam. Okay, a complicated word problem, like building a house or two cars, da-da-da. Okay. However, bear in mind that things like position, velocity, acceleration, that's fair all the time. All right. But after this Wednesday, no more build a house or two cars or whatever problems. Okay, even on the final. Okay. So for many people, Wednesday's your last potentially horrific test. Right, for many of you. All right. Example, projectiles, rectilinear motion. All right, projectiles. Speaking of exams. All right. Well, I just mentioned this, right? So before, in chapter 4, we talked about this position function, S, right? Okay, S for position. And then we took the derivative, right? S prime is V, which is what? That's velocity. And then the derivative. The second derivative of S, the first derivative of V is A, for acceleration. Very simply, in chapter 4, we went down. In chapter 5, we're going to go up. Okay, in chapter 5, we're going to go up the ladder, not down. All right. Okay. By the way, some sample units, like in the problem I'm going to give you, all right? Position is going to be in feet. Velocity is going to be in feet per second. Okay, I know sometimes it's miles. This time it's going to be feet. Okay, and acceleration in this problem is going to be feet per second per second. Although, like when you hear a car commercial, they tell you this car goes from 0 to 60 in 5 seconds. Then you can quickly find miles per hour per second. Right. The average acceleration. That means the average acceleration is 12 miles per hour per second. All right. Okay, so those are going to be the units for our problem now. So here's our problem. Okay, so you're very mad. It's an event. Okay, you go to the top of a building. All right, so here's you. Let's say you're lying down. I can't draw a line. Okay. You're lying down, okay, on top of this building. This building is 100 feet tall. Not this one, but okay, let's say I have a building that's 100 feet tall. 100-foot tall building, okay? And you have this big, thick calculus book you're going to throw down on my foot. So here's me, good looking me, with my foot hanging out there. I'm just daring you to bash my foot in, all right? Okay, and you're mad. You're going to push it down. You're not going to lob it up. You're going to push it down. You're mad. Okay, so you're mad. There you go. You're mad. Okay, you have the Necronomicon. Maybe that's the Necronomicon. Yes, I saw Evil Dead last weekend. All right. Okay. At time 0, we'll just call it time 0. At time t equals 0, okay, you're throwing down. Okay, you throw down the book or brick. Okay, at 10 feet per second. You're throwing it down at 10 feet per second. Okay, that's the initial speed. Notice I said initial speed. You throw down the book at 10 feet per second. That's the initial speed. All right. Okay, now we would like to know what the Big Daddy S function is, and then we can ask questions like in my case, you know, how long will it be until the book is my foot? And can I do the calculation fast enough? All right. All right. Now, okay, well, what is the function? What's the Big Daddy we're looking for? Let S of t be, the position function here is a height function, right? It's the height of the brick or book, right? It's the height of the book, t seconds, it's going to be in seconds, t seconds after it's thrown. Okay. In principle, you could even give it a horizontal push, but we're still tracing only the height. So in that sense, it's still a rectilinear problem, even if you give it a push. We're just looking at height, not the horizontal distance. All right. So what is the differential equation that we have to solve? All right. We have to solve the following. Okay, solve A of t, okay, because there is something that's constant. Okay, A of t equals the opposite of g. What's g? It's a constant of what kind of force? Gravity. It's the local gravitational constant for Earth. Okay, for Earth, it's what 30? It's 32 feet per second about. On the moon, it's different. Actually, even on Earth, it's different on different parts of the planet, right? Because we do not live on a perfect sphere. Okay, we wouldn't want to live on a perfect sphere. Okay, but let's say it is constant on Earth. Okay, little a of t is the opposite of g. That's the local gravitational constant. I will tell you what it is. All right, a of t is about, again, negative 32 in feet per second per second. All right. So a of t is about negative 32 feet per second per second. Why is acceleration negative? That indicates the fact that, well, okay, what's the deal? Here's s, here's v, here's a. Let's say I'm v, I'm velocity, I'm a little child. I'm v, I'm velocity. Here's a, my derivative. My derivative is negative. What am I doing? Okay, if my derivative is negative, then I'm decreasing. But Archie's also right. It means the brick is speeding up because velocity is negative. Remember, if velocity is negative and decreasing, that means it's actually speeding up. Okay, so yeah, it was right here. Okay, right. That's why acceleration is negative. Of course, you know, if you lob the book up, right, it slows down, and then it goes negative in velocity. Right? Zero, then negative in velocity. All right, negative velocity means you go down. Okay. By the way, in case you're curious, in meters, it's about negative 9.8 meters per second per second. Okay, some people just write s squared. Okay. Anyway, so look over there. That is our second order differential equation, right? Because ultimately we want to get the s, right? But what are our initial conditions? Make sure you get these right. Okay, subject to or such that. Okay, subject to or such that. What are our initial conditions? Okay. The fact that the building is 100 feet tall, and you're kind of lying down over there. I don't care if you're tall, so you're lying down over there, right? What is 100 feet? What of what is 100 feet? S of, in particular, S of 0. Right, S of 0. We're calling it the initial time 0. Right, good. S of 0 is 150 feet. Okay? Although bear in mind, you know, there's nothing inherently wrong with saying, hey, let's say it's 4. Maybe it's 4 p.m. There's nothing inherently wrong with that, but normally we start with t equals 0. All right. Now, what else do we know? The book is being thrown down, right? You throw the book down at 10 feet per second. Okay, we're looking at what of what? Not S of 0, but
S prime of 0.
okay, S prime of 0 or V of 0. Right, same thing. Right. S prime of 0 or V of 0. But be careful. It's not 10 feet per second. It's what?
Negative.
Negative. Why negative?
Because it's thrown
It's
down.
being thrown down. Okay. Remember, if you're throwing the book down, then you're throwing it in the quote-unquote wrong direction, the negative direction, which is down. Okay. If you were to lob the book up, you're not as mad. If you lob the book up, it would be positive. But if you're throwing the book down, it's negative 10 feet per second, and if you let it drop, it's 0. You just go like this. Okay, but you're mad, so you're throwing it down. Okay, and these are our initial conditions. In my notes, I just switched the order. All right, good. Any questions so far? So that's part of the problem. Can you even parse the problem so that you know what the differential equation is and what the ICs are? That's part of the battle. Any questions? Make sure you get your signs right. I noticed that some of these problems, a lot of people mess up their signs. So use your head. Okay, be aware of when something's negative. In particular, a rate of change. Oh, okay. That's from physics. That's the local gravitational constant for Earth. On the moon, it's different. On Mars, it's different. I would give this to you on a test. So you don't have to memorize it. I know that physicists were obsessed with trying to measure it accurately. All right. Again, it changes on different parts of the planet. All right, ready to go. Are we ready to solve this second order differential equation? Of course we are. All right. We start with A of t. All right. So we're going to climb up the ladder. We're about climbing today. Okay, A of t is, okay, let's say it's equals. I'm not going to put squiggles. Equals negative 32. All right. So the bottom line, as far as the math goes, let's say A of t is negative 32. Okay. Well, what do I want to do to both sides? Integrate. Okay. With respect to t. All right. Integral of A of t dt equals integral of negative 32 dt. All right. The integral of A of t will give us B of t, and then the plus c we can deal with at the end. All right. Whose derivative is negative 32? Negative 32 t. T is our independent variable here. It's our variable integration. Negative 32t plus c. I'll put a little arrow there to emphasize that. Okay. By the way, if you're obsessed with the power rule, you can think of this as negative 32t to the 0, right? And then when you integrate, you get negative 32t to the first over 1, so the power rule does work. All right. Now, I need to know what c is. Okay, so what do I use? Yeah, the bottom IC. Yeah, let's use the bottom IC. Okay, so let's find capital C. Remember, we know that V of 0 is, what, negative 10. Okay, bear in mind, these are all compatible units. If you have an incompatibility, then convert units. Like if you have meters or inches, feet, to make sure to convert units. All right, but in any case, so from here, right, from here, we get that, okay, we're going to plug in t equals 0 now. We get b of 0 equals negative 32 times 0 plus c. Well, it's typically the case that if you have a polynomial to plug in 0, you're just going to get c equals this guy. Negative 10 equals c. C equals negative 10. All right, plug that in. But again, if you don't have a polynomial, or if you're not plugging in 0, then this might not drop out. Be aware of that. Okay, so then we get what? We get b of t, okay, this is our particular solution, is negative 32t minus 10. Okay, b of t equals negative 32t minus 10. That makes sense. When t is 0, we get negative 10. And in fact, up until the time when the book hits my foot, okay, this tells me the velocity after 1 second, after 2 seconds, after pi seconds, if the book has not yet landed though, right? Because the model's no good when the book's at my foot. All right. Okay, we're not done yet. We want s of t, not b of t, in the end. Although this might help me for other questions, right? What do I want to do to both sides? Integrate. Once again, integrate. All right. So we integrate b of t dt equals integral negative 32t minus 10 dt. Remember, we need grouping symbols because we have more than one term there. All right. When we integrate b of t, we get s of t plus, I should really put what? Plus, yeah, put like plus d. Try not to put plus c because there's certainly no guarantee that c is going to be negative 10 again. So put plus d here. All right. Well, let's work this out. Okay, so here we have negative 32, integrate t squared over 2. Whose derivative is negative 10? Negative 10 t. Make sure to curl your t so as to not confuse it with a plus sign. All right. What's s of t? S of t as a general solution. Okay, we get s of t equals negative 16t squared, negative minus 10t, plus d. Okay?
Would you deduct points for not putting that second step?
You need this here?
Yeah.
You really should put it, but I typically don't mark off. As a matter of good form, you should put it though. You might have to. Questions. some of you might think, hey, this looks pretty familiar. Yeah, well, we'll talk about that. All right. I need to find what? Find D. Who's going to help me? Top one. Yeah. S of 0 equals 100. You need to use this. All right. Okay, so if we plug in t equals 0, because we have s of 0. Bear in mind, I could very well give you s of 1. You know, where is the book 1 second after it's been dropped? I could very well give you that. Here, I give you s of 0, basically. All right, s of 0 equals, well, you see what's going to happen, negative 16 times 0 squared minus 10 times 0 plus d. All right, s of 0 is 100 equals d. d equals 100. Plug that in. Don't forget to plug it in. All right. And finally, we get s of t equals the negative 16t squared minus 10t plus 100. You can see behind this. All right. S of t equals negative 16t squared minus 10t plus 100. That's good from the time the book is thrown to the time the book hits my foot. So in a way, it's kind of funny. Here we find the domain later. If you want to know the domain for this function, you find out when it hits my foot. You set that equal to 0, and that gives you the upper bound on the domain. All right, so we find the domain later, actually. And then I guess the book is at 0 forever. Unless you throw a really heavy book, then I guess it goes to my foot. That's what it comes to the ground. All right. Any questions? Some of you physics people might go, hey, we remember formulas for this. Can we just write down that with no work? No, show me all the work. Okay. I know you have that formula in physics. Yeah. This is S naught, that's V naught, whatever. But no. You can't appeal to your physics class. You have to work it all out. All right, show all work. Show all work. All right, any questions? Any questions? Bear in mind, your formulas work if you're given the initial position of velocity. All right. Any questions? Okay, any questions? That's 5-1, okay. We'll start 5-2 after the test. Okay.
So all you were looking for was a position formula, you didn't have to find t?
Well, of course, I can ask that question on a test or later on, right? I can ask that, yeah. When does the brick hit my foot? Set that equal to 0, right? And then you maybe you can factor, maybe use a QF. Here you'll probably use a QF. Direct formula. Right. Take the positive loop, right? Of course, negative values of t don't make sense at this point. Not that negative values never have the possibility of mattering, but here t has to be non-negative.
So I apologize. So where in this whole thing did it say that was what you were looking for? Was that formula?
Yeah, oh yeah, you remember when I said the word solve. Yeah. Oh, that's a good point. I mean on the test I'd be more precise. What is the position function rule? Yeah, I'd be more precise. Right.
And all I wrote down is solve a of t is equal to.
So yeah, it's like Jeopardy. What question does this answer? Find the position function rule S of t. Okay. And again, the domain we don't know until later, right? The domain of S is bracket 0, comma t star. What's t star? This solves S of t equals 0. Okay, so this is one of those weird cases where you don't know the domain until you've worked out what S of t is. Then you can find out at what time does the brick hit my foot, and then that tells you what the effective, practical domain is. And then, maybe say S of t is 0 afterwards. And by the way, what does this thing look like? I can stick it here, right? T, S of t, right? Well, it's basically going to be a downward parabola, okay? But the vertex, bear in mind, there's no vertex because the book's always going down, right? So there's no vertex in here, right? The vertex is over here somewhere. But this doesn't matter. Okay. And then here's t star. Okay. So the domain of the position function is from 0 to t star. Bear in mind, you don't see this parabola visually, right? Because we're graphing position or height against time. You never see something that's graphed against time, right? Not physically, no. Not visually. All right. and by the way, we can ask what time is it at my foot, also at what velocity is it at my foot, because once you find out what this time is, you can plug it in, and then you can get the velocity at which it hits my foot. Take the absolute value, you get the speed at which it hits my foot. Enough about my foot, but any questions?
Is this the final answer?
Yeah, well, yeah, on the test, I would say something like, find the position function rule S of t. Okay.
And you would just give that formula. Or not.
Will you find it?
Oh, actually find a number.
Will you ask,
You find the formula.
will you ask for the domain too?
That's fair, sure, that's fair. Right. Of course, you know that t is not negative, right, because you know it's thrown at time 0. Bear in mind, if it's coming down from an airplane, bear in mind, t equals 0 does not have to be a special time, but here it is. We're saying, okay, t equals 0, that's when we're letting thing go, or throwing them, okay? T star you can find, right, using the quadratic formula, you can find t star, so that's the upper bound on the domain, all right? And then, also, you can find out the velocity, and then the speed at which the book hits my foot. So you can answer these interesting questions.